concept of like ACR and DCR. Yeah. So first I will like try to go through the content like in a brief way, and we'll jump into the main topic. So first we'll try to understand like what is like ACR or like sorry, DCR and ACR, and what would be like EIS on the battery, and cell ECM, that is nothing but like equivalent circuit models by ECM or like EIS data you can take. Yeah. And understanding the EIS based ECM model system. So equivalent circuit. So all these components, like whatever you see under the fourth one, right? Like charge transfer resistance, double X, solution resistance. We'll try to touch base, like how we can, how these are represented with the electrical system. Okay. And finally, like some result discussion, like which we obtain from the model. Okay. Like we have built the, like we have collected the data from the EIS like test, like from the impedance test, and we collected RC parameters. And those RC parameters, again, we fed it to the equivalent circuit model. And whatever the result we got, and we are going to compare with the real-time test data. So those results, in a basic way, we can like discuss. Yeah. So this is like overview. And we'll also try to understand like what kind of machines can be used like to conduct DCIR, ACR, and how the like the cell has can be adjusted in a machine. So all this can be touch based. Yeah. So first, like the DCR is the long form of the DCR is like direct current internal resistance. So what they want to achieve with this DCR? Okay. So let me pen here. Yeah. So like let's say like you have cell testing machine. So eventually it looks like something like this, right? So this is like DCR testing machine. So you can see some cells has been arranged at the machine. Okay. So according to the pole, like whether it's a positive or negative, like we have to adjust, and we can conduct the tests. So the like again under the DCR, like there are different types of tests. So I'm not going to discuss those. Like yeah, we'll simply take it as like some test names like static capacity test or HPCC test. So those can be like conducted into the machine, and basic charging and discharging again with our required charging profiles can be adjusted. Okay. Yeah. So typically you are like applying the DC current for the cell, either for the discharging or for the charging. Okay. So when you do it, like you can see the changes in the voltage response, right? So like let's say like you have applied the some step current kind of. Okay. You can see this profile. This is nothing but a current profile representing the graph. So this is the output, or this is nothing but like voltage versus time. That is the response from the cell. Yeah. So this is how the voltage response it is going to appear. From these, with the help of like Ohm's law, we can like extract or like RC parameters. Eventually, those are nothing but like your R0, R1, R3, and capacitance, those data. So with that, you can like model the cell like using the equation like let's say like, so the final voltage response will be nothing but your terminal voltage. So OCV, that is open circuit voltage, minus voltage drop at R1, voltage drop at R2. Like when you subtract these things, right, like you are going to get UT, that is terminal voltage, right? So with the help of these data, like you are going to develop the cell model, and this is what you get as a response. So this is like a DCR based testing and getting the data and developing the cell model. Okay. So the same way, like there is ACI. Uh, Sandeep, just a caution here, like you are not supposed to send any kind of request for the screen control here. Okay. Yeah. The same method. Okay. Yeah. So the next thing is like you can see the difference like ECM circuits, this is electrical systems, you can say, like the range model, Thevenin, that is nothing but your one RC, two RCs, or like you can call it as DP. So if you like observe cleanly that you can see like the elements such as like R and C, like resistance and capacitance. So basically it contains like RC parameters, sorry, RC links, you can say. Yeah. And this is nothing but your OCV, and this will be your terminal voltage. But the rest in the bit in between, like you can see them as RC links. So with a DCR, you can extract the RC parameter from your like voltage response. Like voltage response, what you get from the DCR testing, and you can max you can extract the RC parameters. You cannot extract any other behavior of the cell. Okay. So yeah, you want to if you want to capture those behavior, like uh, there comes like ACR. Yeah. So before like discussing like what all other behaviors can be captured, so you will try to understand like what is ACR. Here, like uh, let's say like a cell in the DCR, we used to like charge or discharge, or we used to apply the pulse current, which is the DC current. So we used to get the output. But here we are going to provide the AC current at some particular frequency. So, like varying the frequencies, the travel of the current and the output is going to vary, right? Yeah. So here, like the reason for applying the alternating current is to test the resistance of the battery, and eventually it will eliminate the impact of the polarization. So with this, you can directly measure the resistance of the properties, or like of the cell. Okay. The components of the cell. So where it takes or like it takes very less time in terms of other benefits, if I want to say, like it is not a time consuming thing. Yeah. So you can bring it to some particular SOCs or the capacity, and you can conduct this test. So this ACR testing, again, like further like testing at some particular frequency. Let's take like 1 kilohertz. And then there is EI sweep, electro spectroscopy, electro, yeah, yes, spectroscopy. Okay. So let me electro impedance spectroscopy, or like spectrum. Okay. Yeah. So here, like EI sweep is nothing but like applying the AC current, like the impedance, measuring the impedance at the different frequencies by applying the AC current at the different frequencies. Okay. So what could be the frequency range, and in what frequency ranges, like what all things can be captured? So that we can discuss in the further part of the session. Okay. Yeah. So basically you can just take it as like applying AC current and to the system and getting the output. Like either it can be like potential or current. So based on the what input you are feeding. Yeah. So again, there is a different thing like potential and current application in the ACR. We call it as like galvanostatic and potential static. Like that, I'm not going to cover here. Like we can take the different top boot camp for that. Yeah. So here about the EIS, like the same thing, like conducting the test at the different frequency. That is what we call it as like EIS sweep. So typically the machine you can see, it is a like machine from a company called like IOKI, uh, and where you can see like 4 wires with the probes coming in contact with this particular cell. This is picked from our lab. Okay. And here you can see the H source, or here you can see like properly the L source. There is like two pins, like two pins, you can say. You can see here properly, which is going to come in contact with a cell. So the purpose of this 4 probe like is to one probe like is to capture the resistance of the cell, and one one the other probe is to like measure the resistance of the cable. So even that has some resistance, right? If anything, there is a metal, there will be some resistance. So obviously the cables like will be having the metal inside it, like so it has some resistance. So that has to be taken care. So that is why like a 4 probe measuring system is used. Yeah. So even if you take some battery testing or like cell testing machines, there will be like 4 probes. Like 2 will be for voltage and 2 will be for like current separately. Okay. Yeah. So yeah, that is the difference. So here, okay. So this is the machine, and with this you can conduct uh, EIS and even the impedance test, particular frequencies, and EIS sweep. So this has some limits, like in terms of frequency range. So yeah, we will like see them in the next part. So again, when you take like ACR based testing and collecting this impedance data, right? So again, you are going to like get the data and represent it with the electrical system itself. Similarly, like R naught, R1, like C1. Okay. Yeah. OCV, and this could be the terminal voltage. So this R naught, like typically we say it as uh, solution resistance or electrolyte resistance. So then there is a R1, and one more RC block will be there. That you can call it as like first RC block. Like I have that thing here. So let me go there and come back here. So you can see here, this you can take it as like R naught, RAC, CP, RCT, CP electrode, Waghburg. Okay. So the ohmic resistance or like electrolyte resistance, surface electrode interface. So this is something, a layer which is going to be produced on on the electrode, that is nothing but your inside the cell. When it is taken for the charging or discharging, over the period that layer is going to increase the thickness of that layer. Okay, that also adds resistance. So even that is represented with an RC. And this is like charge transfer resistance, where like the polarization or related term, you can it can be covered. And this Warburg is due to the diffusion of ions into the electrode. So yeah. So then there are some other circuits, Randall's. We call them is as a Randall circuits. Like whatever the ACR based data we get and we represent, we can use the Randall circuits. There is one more element that we can call it as like inductor. There will be some like inductor behavior can be also seen on the cell. So yeah, so I'll just go back. So these are some elements you can see. Like the resistance can be represented with this symbol, capacitor with this symbol, and inductor. So represent magnetic inductance. So Wagner element, sorry, electrons, ions in the solid phase. So constant phase element, non-ideal capacitor. And there is a Grecius element, like which I have not covered here. Okay, the electrochemical reaction coupled with a chemical reaction. So yeah, even yeah, this is also one of the behavior can be represented. So in order to calculate this, like a different set of equations are there. So for that, again, we'll try to bring one more boot camp, because that is again a depth concept. Yeah. So here, like you can see the electrochemical systems, like equivalent circuits. You can say like this is like simple random, like similar like current model. Like one, there will be like RC. So this is something you can see the Nyquist plot. Okay, so I'll just when you conduct EIS sweep, right? Like whatever the output we get, like those data, with that we can uh, bring some Bode plot or the Nyquist plots. Okay, so this is how they appear, the Nyquist plots. Like I'll try to show them with our data, like at the end of the session. Okay, yeah. So again, this is the RC link with attached resistance, that you can take it as like electrolyte resistance. So again, this can be represented over here. So the next, yeah, now the Warburg. So you can see a semicircle, and then there is a 45-degree inclination on the graph. So not every time it can be the 45. It will take some angle. It is again due to some reactions. So again, those can be represented with a different name of the Warburg, finite, infinite, or something like that. So yeah, and then you can take this pick like electrolyte, AC resistance, charge transfer resistance, the two semicircles will be formed, and Warburg. Okay, so like why the purpose of this representing, showing the single RC and RC with the resistors, and like RC with Warburg. and 2 RCs with warp. So not all these elements captured at the same frequency. That is the thing we need to keep in mind. Like all these elements will be captured at the different frequency. Like when you try to conduct, the EI sweep, so it is going to like apply the AC current to the cell at the different frequency and try to capture the resistance. Sorry, the impedance or like a resistance. Yeah. So here you can see this is something at the higher frequencies. You will be able to see the inductive behavior, which can be uh, represented with the L and the ohmic resistance and solid state interface. The semicircle is not like properly visible, but we can understand. Like yeah, again it depends on like at what SOC the cell is, all the stuff. And then there is a inclination, so where the warp can be captured at the low frequencies. So we will try to define some frequency range. So typically, like for NMC, we have worked for the NMC chemistry, 0.01 hertz to at least like 5K hertz. So we can capture all these behavior, like whatever we are able to see. This one, this one, this one, this one, and this one. Okay. Yeah. 0.01 hertz to 5 kilohertz. So like the one you are able to see in our picture, right? This one. This has some limitation, like this machine having the frequency range about like 0.1 hertz to 1050 hertz. Okay. So the two elements, one is inductive behavior and half of the electrolyte resistance. And then there is a other one, the Warburg impedance. So those things are captured at extreme, like not extreme, like ultra high frequencies and ultra low frequencies. So if I want to define here, so you can see the low frequencies. So this one, like low frequencies, like it should be ultra low frequency. Like you can say is you can take it as like 0.01 hertz. So there you can able to capture the Warburg. So yeah, with a 0.1 hertz or something like that, you are able to capture only like half of the Warburg, where it won't like completely carries out the behavior of the cell. Okay. And when you take high frequency, right? So our machine is having like around 1 kilohertz, like 1050 something. Yeah. We can capture about like half of the up to half of ohmic resistance, like not complete graph. So inductor behavior, like you can neglect. Again, it depends on the chemistry. So if you try to take like 0.01 hertz, we can capture like all the behaviors. So this you can take it as like ultra low frequency. Yeah. So in this way, like these at the different frequencies, if you try to conduct and will try to capture all these impedances. Okay. So the next thing, this is the same like which I was explaining, that is ohmic resistance, surface electrode influence, charge transfer. Yeah. So let me, yeah. So let me go through some results. So I'll just try to use this result. So this is the real-time test data, and the one with the blue you can see like Randall 1RC model. So in this model, like I don't think we have included inductor behavior because of the limitation of that machine and also the Warburg. Okay, it is typical like 1RC means it is similar like Thevenin itself. It is Thevenin itself, like R naught, R1. Yeah. So this will be electrolyte resistance, not electrolyte, like, yeah. And this will be RCT and CPE. And whatever you get like output will be terminal voltage. And this will be OCV. So this will be the 1RC random circuits. You can take it as like simple random circuit. In the complex random circuit, you will be including like other than RC elements such as like inductor, like there one more was like Grisha's element, Warburg element. Okay, yeah. So you can see there we are not able to see like complete overlap on the results, but somehow like we have achieved like more than like 97% of accuracy here with this model. When we try to include the inductor behavior and the Warburg, like we can reduce this error also. Okay, yeah. So I'll just try to show some of the results from my system. Okay, like the Nyquist plots, which I conducted for at the different SOCs. So just give me a second. I'll just share that particular file. So meanwhile, if you have any questions, you can just put it in the chat box, or like we'll try to discuss them, or we can take it at the last itself. Yeah, I'll just share the screen. Yeah, I hope this came visible. So we took the 5% as an interval, uh, as a capacity of the SOC you can take. So yeah, we'll just try to show you like from 100%. This is the graph from the machine what we can see here. So yes, okay. So again, like if I take it to 50%, there will be some changes. Yeah, these are like Nyquist plots. And if I take to 0%, and you can see the result is somewhat different, right? So from these, how we can capture like RC parameters from these Nyquist plots. So there are some set of equations. For that, I will plan to take some other web bootcamp for that one because it is again we need to go deep into this concept. Yeah. So if the people not interested in those like going for the equations, and if they want the direct, there are some tools available. Okay, yeah. So those tools I'll just try to show you over here. So I hope you can see the screen. Yeah. Something called like circuit fitting. So we just need to select impedance data. So what I'm going to do, I'll just browse to my data where I kept. Yeah. Let me take like, yeah, any random data. So I'll just select this Excel sheet, like which is having all the like impedance data. I'll just say open. So it will take some time. So this particular circuit fitting, right? For this particular element, sorry, like you can take it as like electrical system. It will fit it and it will try to provide the data for these RCs, W1, R0, all the stuff. Yeah, it will take some time. Then there are like many tools. There are some paid versions or some, yeah. So even those can be used. After this, like I'll try to show you how the data we get from the machine. Okay. So we will try to wait for like 1 more minute. We'll try to see. Yeah. Don't know why it is taking so much of time. Anyhow, like, okay, I'll just show you the data. We go back here, just a second. Yeah, this is the data, like we got, okay, R0, R1, L3, CP, CP2, W1. So, right, at the different SOCs, we captured and whatever the data we got, right, I'll just try to plot one graph here. Yeah, and yeah, you can see SOC versus R0. So these curve, like we are going to feed into our cell model, uh, which we built in the MATLAB and Simulink, and then we can like give some current profile and get the output. Okay. So with the help of lookup tables, we can build this data setup. So let me check whether we got. Okay. Yeah. Now you can see. So there is a Nyquist plot. You people call it is also called like pole plot. So there is a data and the fitting. So the data is what we fed and the like the exact fitting will happen. So you cannot see like 100% overlapping. Okay. Yeah. And these are the model datas. Okay. This is like particular equation. And these are the parameters. So in this way, you can uh, capture, you can make use of these tools or like whatever the data you collected from the machine and you can like get the data. So yes, yeah, there is option of like downloading them. So yeah, this is it is just going to give in Excel sheet format. Just cancel this one. So if you are not satisfied with the curve, you can again reconduct it. So then there are like many applications like ZView, ZVim or something like that. So yeah, they work similarly. So for this circuit fitting, there it is a fixed element. if you want to change this RC element, right? So then there is a different uh, tool like where you can build your own RC, and you can accordingly you can fit and correct the data.